Okay, welcome back everybody. So we're going to pick up where we left off. We had written down the statement for Cramer Rao. It's on the board. Let me just tell you what this means again. So this is a theoretical statement for a lower bound on variance. Sometimes this lower bound is useful, and certain estimators obtain this lower bound. So the lower bound is on the right-hand side. So this is talking about some arbitrary test stat with all of the data in there, and it's saying what the lower bound on the variance for that test stat is. It's not super useful the way that it's written, except in certain cases. So we have this statement about this arbitrary thing over here on the right-hand side. If this was a function of the parameter, let's say it was theta. So I was talking about W such that the expectation of W was always theta, then I can say something about this because it's a function of theta and not this arbitrary test stat. So if this was equal to theta, then Wx is unbiased. And that's probably the most familiar case of using this bound right here. So I could say, in the case of unbiased estimators, so if this was true, if it's, is unbiased. So in the case of unbiased estimators, my variance bound would just be bounded by this, right here. So logarithm f of all of the data, however many data points in there. So the asymptotics are built into this through n data points from the distribution f. So squared, and this is inverted. So this has a name. This is called the Fisher information. And sometimes we write this down as pi theta. So it's a function of theta. Keep in mind when we're taking the expectation, we're taking it with respect to x. So the x's are out of the equation. And so this is a function of theta. So the Cramer Rao lower bound says in the case of unbiased estimators, if I wanted to constrict myself to the class of unbiased estimators, I could know theoretically what the lowest bound on variance is. So now we can start talking about, in some sense, optimal estimators. So if I were considering the L2 norm. So if I were working in the L2 loss function, we've seen the bias variance decomposition. So bias squared plus variance is MSE. So if I knew that an estimator was unbiased and I wanted to constrict myself to that class, the bias would be 0. So 0 squared is 0 plus variance. That's the only remaining term. And so in the class of unbiased estimators, if I wanted an optimal estimator with respect to the L2 norm, i.e. MSE, then it would amount to finding an estimator in that class that minimizes the variance. So this is a useful tool for maybe being able to theoretically say what the lowest unbiased estimator's variance could be. So that's kind of cool. And in some cases, estimators actually attain this lower bound. So if you have an estimator that attains this lower bound, you don't need to search for any more of them. Now, Sai came up with an interesting comment, and I think this is a familiar comment. I think I've been asked this every single year I've taught this class. Well, what about other estimators out there that I can reduce the bias, or I can add a little bit of bias and reduce the variance a little bit more? So this doesn't address that exactly. Sometimes you get lucky, and you might say, I want an unbiased estimator that reduces the MSE, and it happens to be the minimal variance estimator that also happens to be unbiased. But you would have to take another direction to really verify that. We've seen examples where we've added a little bit of bias and reduced the variance. So, and brought down maybe the MSE. So sigma squared estimators for that, there's an example just like that, that if I look in the class of unbiased estimators, they're maybe not, or unbiased estimators, there's probably other estimators out there that beat the MSE. There's certainly estimators that I can bring down the variance, but also there's estimators out there where I can bring down the totality of the MSE itself. So just keep in mind, I think that people abuse this statement of the variance bias trade-off, and they start thinking about that equation, bias squared plus variance. They're like, that's the whole entire thing, but there's a misconception that the variance is locked in, or the MSE is always locked in, so you're always dealing with that same MSE. Sometimes you can bring down that MSE even by inducing a little bit of bias. But this is at least a step in the right direction that we can verify in certain subclasses of estimators that they're optimal in some sense. I will point out, if you want to know more about this sort of stuff, you're looking for an advanced inference class, and they'll certainly walk you through that Lehman-Sheff-based stuff and tell you more about completeness. So completeness is the segue we need to generalize this a little bit further. And I'm not going to go over that in this class. I just want you to know that it's out there, and there are some examples in the book. So you can look at those if you're interested. If you use that, those sort of theorems that appear in the book using completeness, and you use those to prove optimality, I'll set that to you. So I'm probably, for the purposes of this class, going to tell you, I'm going to ask you questions like, does a certain estimator reach the Cramer Rao lower bound? Is it optimal in the class of unbiased estimators? So in the class of unbiased estimators, this thing right here is 1. So the numerator. You could certainly apply this to other cases where I could say, well, I'm going to look in the class of certain biased estimators with certain bias levels. So you can imagine maybe if this was 2 theta or something like that, and I take the derivative, it's 2. So there's some bias level it's doubling the estimate. So I guess you could sit there and do that and say in estimators that, you know, have a bias of 2 or something like that. What is the lowest variance estimator? I've never seen anybody actually do that that could do that, but there are common applications, and I'd say the most common application is to apply this to unbiased estimators. In normality, things are really nice. You get a lot of things for free. I could go find the minimal variance estimator out there, and then I can verify that it's probably unbiased as well. And so the normal thing is a little bit too optimistic. Everybody agrees on the right estimators for mu in a normal distribution. It's X bar, and it enjoys a lot of properties. So it is the minimal MSE estimator, it's unbiased, and it's minimal variance. So you get all 3 things. So, which is really awesome. And X bar pops up a lot in asymptotic normal exercises. So that whole central limit theorem thing is really awesome. Okay, I want to prove this lower bound to you. I also want to run through an example just so we can see how to use this. I will point out, here's a fact, that I can rewrite the denominator of this like that if something is true. So let's just fill in the ifs real quickly. So this statement is true if this is true. Expectation of Wx is equal to the integral of the derivative Wx f of x given theta dx. So this is basically just saying I can interchange these operators. So that's Houdini's theorem. A good example of where you can't do that would be like the uniform 0 theta, because theta would appear on the bound of the integration. You can't just slide that derivative right by. So the normal example is a good example where you can slide the derivative right through. This is true. So if that same thing is true, so I'll just write down that this is star. That's going to be our important condition. So if star is true, this is also true. So when Cramer Rao applies, you can use this identity. So also, this is kind of the more trivial assumption, is that the variance that you're even looking at exists. So if we're going to come up with a lower bound for this thing and talk about it meaningfully, it better exist in the first place. So this proof does not apply to things where variance doesn't exist because you wouldn't use it in the first place. So a good example of that would be a Cauchy distribution. Cool. Real quick, how would you prove this? Somebody gives you a statement like that, what would you do with it? Should we do a quiz? What would you do? Yeah. Check the left side, write it out. Write the right-hand side, check them both, and make sure that they're the same. They don't look exactly the same. So obviously there's something going on in these equations when you write them out, but there's some zero in there somewhere. And so basically, you're just gonna do this thing. You basically take your two derivatives, expand what it looks like. So that's not a big deal. So you probably take your first derivative. Then when you take your second derivative, it's going to expand into two parts. So when I take the derivative of the log of f of x, it's going to be the inverse of f of x given theta times the derivative of f of x given theta. It's just a chain rule. So when I take my second derivative, I'm going to apply maybe the product rule is the way I like to think about it. If you like the quotient rule, that's okay. But it's going to break this into two terms. And so there's only one term over here on the left-hand side. So one of those terms, after I take the second derivative, is zero. So that's what you're actually would prove. How do you prove it? You have to use star. So there's basically an integral out there with a derivative inside of it. You can see that derivative inside. So I pull that derivative outside of the integral. And when I pull the derivative outside of the integral, I can verify that the derivative of that integral is zero. Basically, you're going to be integrating over a constant. And so it's going to be a constant. You're going to be integrating over something that's a constant. I'll tell you what you integrate over. You integrate over the sampling distribution. It integrates to 1. Take the derivative of that is 0. So those are the steps in my mind, but all you have to do is just work through this thing, show me where the zero term is, and show me that everything that's left over is equivalent to that. So if anybody ever hands you an identity and asks you how do you prove it, you chisel away at the left and the right-hand side until they look the same. So I'm going to ask you to do this probably on the midterm. We can maybe talk about that at tomorrow's review session. So I would say this gives you some direction to kind of plow down, do something, and if you cannot answer that, I'll try to walk through some of the steps. If I walk through all of the steps, I won't use it as a midterm question anymore. So I think that's pretty straightforward since it's in every inference book I've ever familiarized myself with. You can certainly find this online, so plenty of resources out there. So I hope to use this as a midterm question and just say, prove this identity to me real quick. And then you guys know how to do it. Fair enough? Cool. We're going to use that identity today because it's going to simplify things. Usually I like taking the second derivative rather than squaring this thing out. So very often I can imagine that maybe if I took the derivative and this was like some polynomial term or two terms in here, and I square it out and everything gets expanded, that could be pretty grotesque. A lot of times when you're taking the log of something and you're taking derivatives over that, every time you take a derivative, something goes to 0. So that's kind of nice. So very often you get a simpler format of using this. I also get a lot of insight out of looking at these two equations right here. So conceptually, I kind of like thinking about this thing right here. Because in calculus class, they told me stuff about second derivatives. They told me that it had to do with how convex the shape was. Was it really peaky or was it really flat? And so that's really what it's talking about. It's I guess the word I was looking for is curvature. So how curved is this space? So if it's really peaky, it's really curved, and if it's really flat, it's not recurved. So that measures this. So there's a little bit of intuition. If I think about this, and I just think about this term right here, that kind of makes sense that the curvature, if I ended up replacing this with the second derivative form, that the expected second derivative, the curvature of that space has something to do with the variance, which is kind of cool. And they're inversely related. So, and that's kind of cool. As the curvature goes down on something, it's getting flatter and flatter, and there's more and more variance. So I kind of like thinking about that. So, and replacing this with the second derivative form. So, because I get it, there's some curvature in here, and that's related to variance. So that makes sense to me. I can't quite see this in this form. One thing I like about this form is it tells me that this creature right here is always positive. So this is positive. So that's a bit of a relief, because I'm using it to bound variance. So if that thing was negative and popping up, that would be absolutely useless to us. So it's guaranteed to be positive. And that tells me another thing, that if these two things are equal, and I'll remind us again, Fubini's has to hold for this to be true. So you need this condition. If Fubini's doesn't hold, you won't be able to prove that statement, and it's just not true. So be careful with that. But I like thinking about this thing as positive, but also I get a sanity check that if I do work through this whole equation and I get something that's not positive, I know I've made a mistake. So that's guaranteed. So if you're ever working through the Fisher information and it turns out to be negative, you have a calculation error. Or you've used this formula when it doesn't apply. So I'll just point out, this right here is I theta. That's always true. So that's the Fisher information under any case. If Fubini's holds, then I can also use that and substitute that in for the Fisher info. Cool. Let's say the proof for that statement is probably like 4 lines. So probably be done in 1 line, but I'd rather see the 4 lines. You just go through the steps. So Dylan's like, I'll do it in 1 line. Boom. Yeah, A is equal to A, so A is equal to A. It's tautology. Not won't fly. Just heads up. So I need to see a few little lines to convince me. Okay, let's look at an example. This is where we left off last time. So xi is coming from a Poisson distribution. We know what Poisson looks like. Probability, I'll write it like this, of x, but this is just a probability statement. Given lambda is e to the minus lambda to the x over x factorial. So the x's are counts. And the rate parameter is positive. If it's 0, you get a point max at 0. That's what you get. So maybe you could think, hey, that's useful. I like thinking about that. I probably would have encoded as Poisson with lambda being equal to 0. I'd probably encode that as point max. So that's our distribution. Let me just show you one more thing about this. And you can see this in this form very easily. You can't see it in the quadratic form of this. If xi's are IID, I can rewrite this. So this is f of x I given theta. I goes from 1 to n. So this is the IID case. So Cramer Rao holds in the non-IID case, but in the IID case I can substitute that. So, which is kind of cool. So then I could end up taking this whole thing and rewriting this as sum I goes from 1 to n log of the fxi's given theta. So I can substitute that in for this. And then I can take this summation sign and I can pull it over here because it doesn't have anything to do with the thetas. And then I can pull this summation sign outside here because of Fubini's. So if I can interchange any version of summing things up, no matter how I think about it, I can interchange it in any way. If I can interchange it in the integral form, I can interchange it in the discrete form. And so this thing ends up becoming sum I goes from 1 to n, expectation, 2 derivatives, log of fx I given theta. So point with everything being IID is I can just remove that I. They're identically distributed, so all of the xi's share the same properties. I'm integrating with respect to the same distribution. In this thing, oops, there's a negative sign. Do not forget your negative sign. That's my big trick, to try to remember my negative signs, because I draw them all the time. So leaving negative signs, almost nothing more can mess me up than that. So that's a negative sign here. I can replace everything because of the IID notion of everything, and I can replace that sum with n. So in the IID case, for the Fisher info, all you have to do is work with a one data point analysis, plug that thing in, and then multiply everything by n. That's a little trickier to see here, but this is true as well, that if I ended up just using one data point here, I'd have to multiply by n there. So for the same reasons. So having both of these forms is useful to us. Okay, we're going to use all of that. So I need to work out the Fisher information for lambda. I'm going to write that down as I lambda. So lambda is my theta in our analysis. So this is just a calculus problem. I like it like this. The nice thing is that if you're working through all of this, you're going to take the first derivative first. So you're going to see if taking a second derivative is going to help you out and zero things out. So I like using the second derivative form when things get zeroed out. So if it's zeroing things out, it's always nicer to use this. And you have to take the first derivative in the other form anyway. So you have to do it no matter what. So we'll replace this with that function right there. Oh, and I'm going to write down n right there. So this is just one data point. Fictional data point that I'm averaging over, since this is an integral. So that's what I'm averaging over, x given theta. So this just looks like this, minus n. Again, don't forget that. That's so easy to do. Expectation, 2 derivatives. Let me just rewrite this log a little bit easier. So I'm just going to plug in this equation. So this is going to be, I'm going to just spin these around right here so that I don't have that leading negative sign out here. So this is going to be x log lambda. So that's this part. Minus lambda. So I just didn't want that minus lambda sitting out in front. So I'd probably forget that negative sign as well. And then minus log x factorial. And if you had forgotten about this part, that would be fine. So again, when I'm dealing with the likelihood part of the function, that's my normalizing constant. So just be careful with those. What people are calling constants sometimes aren't constants with respect to every parameterization of the distribution. So 2 derivatives over that. All right, need to put that square there. Everybody good? So this is minus n, expectation. I'll take my first derivative here, so this is going to be x over lambda. This is going to be minus 1. You can already see when I hit this with the second derivative, that's going to disappear. So minus 0. So this is minus n, expectation. I'll take a derivative over this. I always flip that up in my head. This is lambda inverse. So I pull down the minus lambda minus 1, the exponent, and then I increment my exponent. So it looks like that. This is minus 0, if you will. I'll just get rid of that. And we're almost done. So big sigh of relief. The negatives cancel. This thing is positive. So that's my first sanity check right here. This thing turned out to be positive. I must have done something right. So this is plus n over lambda squared, expectation of x. And we know what expectation of x is. It's lambda because it's Poisson. Variance is also lambda. So this is n over lambda. Is the Fisher info. And then to come up with my variance bound, what I need to do is invert it. Don't forget to do that last part where you invert everything. So I've seen that answer a lot. So you're doing all the steps correctly, and probably I would be inclined to mark something like that off if I saw that that wasn't inverted, because I would say, you're telling me that as n gets bigger and bigger, the variance just keeps climbing. So I would think of it as an unthoughtful answer. That would be like the -2 on a homework. That doesn't really penalize you. But come qualified exam time or final exam, I get a little bit worried that you're not thinking about the answers. So the variance here of unbiased estimators, I'll write it like this. It's going to be bounded by lambda over n. So that's how you do this. So that's kind of cool. When it says in the class of unbiased estimators for a Poisson, there is no estimator that has a lower variance than this. So Scotland's variance bound of 0 didn't help us at all. We already knew that. And I might still continue to search. But what we saw last time is that X bar obtains this. So X bar obtains this bound. So I can stop looking for estimators. If you're in an advanced inference class, they might ask you, is there any other estimator out there in the universe that also does this? And if you knew about completeness and things like that, and that's the way I intuitively try to explain completeness, if something wasn't complete, then I said you could get 2 estimators with similar properties. In this case, this test statistic is complete. I'll just throw that out as a comment, and there's no other estimator that does that. So I'm not going to ask you about uniqueness in this class. That's a different thing. You've got some estimator that obtains this, so it's attainable. So in the book, which I'm not going to cover, is a condition on attainment that basically is just unwinding the proof of Cramer Rao. But if I have an estimator that obtains it, I know it's attainable. So, done. So, I won't be devious on a midterm. I just want you to know the general idea and how to use this. So when I see something that asks me, does it match the Cramer Rao lower bound? I first think about this condition. If this condition does not apply, then I say, no. You know, it has nothing to, like, Cramer Rao is not even applicable. If this is true, I work out the Cramer Rao lower bound, then I might work out the variance for my actual estimator. Could be an easy problem, could be a hard problem. Working out the variance, I'm almost always inclined to ask you something about an order statistic since we spend so much time working on them. And so, anyway, just keep that in mind. That's how you use Cramer Rao. Let's prove this. So we want to prove. It's MBOO, so minimal variance, unbiased estimator. Statisticians come up with the worst acronyms. So MBOO. No wonder everybody likes computer science. So that just couldn't even sound it first. Get rid of this. I think I'll just use the left and right panels. Well, maybe maybe I'll just rewrite everything. So Cramer Rao is this. Variance of Wx is greater or equal to derivative of the expectation, Wx squared divided by the Fisher info. And I'll write it out like this. Choices on how I want to write that. I'll pick that form. Okay, we're going to need some facts along the way, so I'm going to build up some facts. The proof in the book interweaves these facts with the proof, and they do a little bit of substitution, so let me try to untangle what they're doing. So they end up deriving some general facts that they just write down that are true if one holds. So I'll just write down one again, or a star again. That the derivative of the expectation of Wx is equal to this interval. Okay, so I'm just going to use the same notation that the book uses in their proof. And I'm just going to talk about some general function. And I think this is the most confusing part of the proof because they use this function to substitute two things into. So they recycle the formula. So, but you can do that. You're allowed to recycle formulas and change what you plug into their inputs. Let me try to explain that a little bit. So here's the first step. Derivative expectation of g of x. And g of x they're going to use as a dummy function. There's going to be two cases that they apply this formula to. They're going to apply it to cases where g of x is equal to 1 or g of x is equal to Wx. So when they switch back to Wx, they're talking about the proof. The specific proof, because that's the W that's on the board already. But I could use formulas and substitute instead of Wx, I could just plug some constant in and see what it evaluates to. So let's just look at that. So this thing right here is just the integral of the derivative. I'll just write it like this. G of x, derivative of f of x given theta. D theta dx. So I didn't change anything. I used to have my derivative sitting right out here when we wrote this thing down. But g of x is just like f of x in the sense that it doesn't have thetas in there, so I can roll that derivative right past it. So nothing funny going on there. So I'm just going to take the derivative here. There's no thetas in this. Just like Wx. Wx doesn't have thetas. If you end up giving me a function with the data and the parameter attached to it, I'm going to say that's not an estimator. So that's one of the top two errors that people make in this class. Is they hand me back where you need to know what the parameter is to create the estimate. And if you do that, I'm going to think, why didn't you just hand me the parameter back? So you don't get to know it, you get to know the x's. So in every case that this is going to be useful, that doesn't depend on theta. You're not allowed to use that when you estimate theta. So just to rewrite, let me rewrite this again. This is g of x, derivative, d theta f of x, given theta. And I'm just going to multiply by a funny form of 1. So I just divided there, multiplied by there. So keep in mind this derivative is only applied to that. Right there. Not here, didn't do anything fantastic. And so I can reinterpret this function as an expectation. This is now an expectation with respect to that. right here. So this is equal to the expectation of g of x times the derivative of f of x given theta divided by f of x given theta. That's all inside my expectation sum. So that's the way I interpret this, is this is just an average with respect to that distribution. So I can rewrite this right here, and I can rewrite this as the derivative with respect to theta of the logarithm. There's our log that's popping up. F of x given theta. So those are the same things. I take the derivative, it's 1 over that function, I apply the chain rule and take the derivative to that function. So this is equal to the expectation of gx times the logarithm of the f of x. Those are the same things. So this is my left-hand side over here. And so long as star holds, so we did apply star because I drove that derivative inside of the integral, then this is equal to this. So let me tell you a general fact. I'm going to substitute in g of x is equal to 1 into this equation. So we're not quite at this proof yet. We're just saying some general stuff. So if I ended up looking at this, d theta expectation of 1, so I'm going to just replace g of x with 1 in this equation. So I'm just entertaining a case, some very specific version of this equation, and coming up with a general statement. So I can take that derivative. That's pretty easy to do, right? What's this? 0. That gets super angry. So, thank you. So I feel relieved. That's 0. We're all on the same page. That's just a constant. So expectation of 1 is just the integral of the sampling distribution, which is 1, so that's 0. So that's telling me that this thing right here, when g of x is equal to 1, I end up having expectation of the logarithm of f of x given theta. This is something you'll encounter a lot. So if Fubini's applies, and I can slide derivatives in and out of this expectation, I know what that is always equal to. I've worked out the left-hand side at 0, and I plugged in g of x is equal to 1, so this thing is 0. That's true so long as Fubini's holds. I don't care what the distribution is. So here's fact 1. Expectation of the logarithm of f of x given theta is equal to 0. So that's true so long as star holds. So anytime I ever see this written down, I know that's just another version of writing 0. You see this in a lot of proofs in statistics. So a lot of things canceling out, a lot of zeros floating around that look just like that. So again, Fubini's has to hold for that to be true, because we used it here. Okay, we're going to use that.
I'm missing something with the derivative of the log. So like I get that 1 over fx is the derivative of the log. Somehow that cancels and you get just 1 over fx.
Oh, you have d side. Yeah.
That's d theta. Sorry, this was d theta log,
Yeah.
and I didn't plug that in here. This is d theta log, right here. I'm missing something. Does that make sense? Cool. That's just another example of your professor data notes.
Should you also need it over there too?
And I need it over here. So this is not a fact. This is a fact. So d theta, so this is important. the derivative of the log of that thing is 0. Okay, cool. We're going to use that. So this is probably the part that confuses people, that people are like, wait, what was G in this group? And they just interweave that in there so that they can make this claim. So they can derive this for you. Probably a better way to do that would be to say aside. Let's just do some math up front. And boom, this is true. Let's use that in a little while. And that's what they are saying. They're just condensing the space that they say. So we've got this fact, this generalizable thing, and we're going to use it. So now I'm going to tell you some other stuff. Now we're going to go back to Wx. And I'm never going to use g of x is equal to 1 or anything like that. I'm just going to consider Wx from now on. So the only place g got used was to derive that. This funny version of 0. I used to think it was rude when people pull out a camera and just start taking a picture of me. It happens all the time. And people walk up to me and just start recording me. So, okay. I better not do anything heinous right now. So feel free to take pictures, take videos if you like. Okay, here's the statement. So the covariance of Wx. Actually, let me just tell you another fact, real quick. So here's just another fact. Forget about what x and y are. This is always true. Covariance divided by the square root of variance of x times the square root of variance of y is going to be equal to some number rho. Does anybody know what this is called? This is correlation. It's the correlation coefficient. Anybody know where that lives? Yeah, exactly. So that's an element between -1 and 1. Okay, so we already know that fact. So if you standardize normal random variables and you take the covariance of it, you really take the correlation. It'll never exceed the normal one. So here's a slightly different fact. This is going to be squared. This is going to be the variance of x times the variance of y. This is exactly the same thing. So I squared it out, I got rid of that negative sign. So I took the square of the left-hand side and I just rearranged everything. And so I knew that the square of something between -1 and 1 is bounded by 1. So it's always positive. They have a name for this. They call this Cauchy-Shwartz. This is Cauchy-Schwartz like you see in your vector calculus class. It is the same sort of equation applied in this specific case. If you don't want to remember it this way and you want to just remember it as this is just a basic statement about correlation parameters, you can do that. So the book calls this Cauchy-Schwartz. I don't care how you think about it. It's basically just a rearrangement of the statement about what correlations are in this context. So now I'm going to take x is equal to Wx. And I'm going to take y is equal to the derivative of the log f of x given theta. So I'm just going to substitute into that formula. So the covariance of Wx derivative logarithm f of x given theta divided by, and I'll write this down as squared, the variance of Wx times the variance of the derivative of the log. I can't help myself, I'll call it likelihood. So this is less than or equal to 1. So really all we have to do is recognize this statement right here is Cramer Rao. So they're identical statements, we just need to chisel away and see that this is just a restatement of that, or vice versa. So let's just do that. So covariance of Wx and the derivative of the log likelihood is just equal to the expectation of the product of those two things. So we're just going back to what the definition of covariance is. Logarithm, so it's derivative of the logarithm, f of x given theta minus the expectation of Wx times the expectation of derivative of log likelihood. So that's what covariance is. If you didn't know, now you know. If you didn't know, you're in the wrong class. So if you ended up just plugging in x and x into that, you'd get back that formula e of x squared minus e of x all squared. So this right here is 0. We've already proved that. So this covariance is this thing. And I have another name for this as well. So what's our other name? I probably should have left this on the board. This whole thing, this term is the derivative d theta expectation of Wx. That was my first line with G, is I had taken that derivative inside of the expectation, I rewrote this and I rewrote that term right here. So that's your first line of everything that we wrote down. So this is another way to recognize this thing was just that thing. That's the first thing we wrote down. So we're kind of starting to see Cramer Rao pop out of this. So this whole equation, I'll call this star star. So star star, already the numerator looks like derivative d theta expectation of Wx. Squared. I'm just going to end up rewriting this part right here, variance. That is the variance that's written over here. I'm going to pull this over here. So this is variance. There's still another term right down here. You'll know what it is in just a second. This is the variance of Wx. So I didn't have to do anything there. That was just this variance. I pull it over here. I rewrite the covariance is that thing because they're the same. And now all I have to look at is this last part right here, variance of that thing. And so let me just rewrite what the variance of that thing looks like. We've got our statement. I think we know what it says. The variance of the derivative d theta log f of x given theta is equal to the expectation of dp theta log f of x given theta squared minus the expectation of the log likelihood all squared. But we already have our fact that that's 0. So this variance right here is just that. And that's the Fisher info. That's I theta. The way we originally wrote it down. And so this thing right here is just I theta. However you want to write it down. You write it like this. Derivative squared log f of x. Boom. That's it. So nothing more to add. This is entirely in your book. I think they crafted the same process. All that they do is a little bit quick in my experience from talking to all the students in this class is what's up with this g function that they keep substituting out. They only sub it once with 1 in wx. So the substitution for 1 was just to give us that fact on the board, the first fact. So the non-fact that we turned into the fact. And that's it. So really, Cramer Rao is just a rewriting of Cauchy-Shwartz where condition 1 holds, i.e. Fubini's holds. And that's pretty good. So practice a few of those problems. Wouldn't be uncommon for me to ask you something like that. What are distributions I usually ask about? Distributions we've touched in this class. So binomial, maybe exponentials. So we have touched gammas. Exponentials are a part of that. So I sometimes like to talk about those. Poissons, normals. So I will not ask you to regurgitate this proof on Friday, but I might ask you to verify that one fact where I can change the first derivative form into the second derivative form of the info. Again, star has to hold for that. That's it for now, you guys. We'll have a review session tomorrow. Happy to answer any of your homework questions. Those homeworks are due on Friday, and we have our midterm on Friday. So yes, no, maybes tomorrow. You can ask me what's on the exam. I've already kind of alluded to it. We'll commit tomorrow. Thanks, y'all. G of x is G of x. When it's G of x happens to be 1, then I have a specific version of that formula. Well, I'm just using the fact, recycling the fact. So I derive this fact. So I just derive this as a fact. If we do holds, I get to keep using it. I probably, the book probably should just derived that fact for you.